All right, so what we want to do now is to evaluate some logarithmic expressions. So I hope you're ready. Make sure that you have your power sheet ready, and let's just kind of go through these as quickly as we can, because they're really not that bad. So let's start here. Let's start with log base 2 of 32. Now remember that the answer to the logarithm is the power. So what's the power that you would apply to 2 to get 32? Well, if you have a hard time thinking about it, imagine that you rewrite it to look like this. 2 to what power is equal to 32? This is the question that you're trying to answer, okay? And if you look at your list of powers, you see that if you go all the way down there, 2 raised to the 5th power is going to equal 32. And this is going to be one of the guys that we see over and over and over again. I like to use this guy a lot. So yeah, make sure you know your powers. The next one we have is log base 5 of 1 over 25. So again, the answer to the log is the power. What's the power of 5 that's going to give me 1 over 25? Well, remember the little trick that we've been playing. If I just do this and I say, what's the power of 5 that gives you 25? You should all tell me that that's the power of 2. 5 squared is 25, right? But to end up in the denominator, you need a negative. So let's make sure we remember and we review how negative powers work. If I say 5 squared, that means 25. I'm supposed to get 1 over 25. So if you think about 5 to the negative second and how we work with negative powers, that means 1 over 5 squared, which becomes 1 over 25. So that's why negative 2 becomes the answer to this logarithm. All right? A couple other quick ones over here. If I have log base 382 of 1. Now something I haven't quite mentioned just yet is how we write our logarithms. Please understand that this is going to be a subscript, so it's going to be just below that baseline for how you write. And this is not a power. This is on the same line as that logarithm. All right, so here the question is really asking, what's the power that you would apply to 382 to get 1? You might say, I don't know my powers for 382. Well, I don't either, but here's what I do know. I do know that almost anything raised to the 0 power is going to be 1. Now, this is, of course, provided that a, the base, does not equal 0. So if I have log base 382 of 1, the answer here is 0. 382 to the 0 power is going to equal 1. Anything to the 0, except for 0, equals 1. If I do log base 17 of 17. Another really quick one that I like to give my students all the time. Think about what this means. 17 to what power is going to equal 17? What's the power that you would apply to 17 to get 17? Well, quite simply, to the first power. See, when we dealt with those exponential functions and equations, previously, we saw this. We saw that when I raise anything to the first power, well, it's just that number itself. So it only stands to reason that 17 to the first is 17, so that's going to be the answer to our logarithmic expression right here. But sometimes the answers are not quite as clear-cut as these. So if I ask you to evaluate log base 7 of the 5th root of 49. Now you could turn this into a big, elaborate exponential equation, and you could say this. I've got to find the power of 7 that's going to equal the 5th root of 49. You can do this and go through the process of solving an exponential equation, but it's actually not that bad. because of this. What's the power of 7 that gives you 49? Well, you know that 7 squared is 49, right? But remember, the answer to the log is the power. So you have to think about this completely in terms of powers. The index of 5 means that for the power, that's the denominator. So the answer is just 2 over 5. Okay? And this is going to work for all kinds of radicals. If I do log base 2 of the 13th root of 32. We could cry about this, or we could just pause and think about what just happened here. First of all, what's the power of 2 that gives you 32? Well, we know that's 5. We saw that up above right here. We know that 2 to the 5th power is 32. Okay? But what about the index? How do I incorporate that in my answer? Well, just like we saw over here, your index is the same as the denominator of your power. And since the answer to the log is your power, the index becomes the denominator of your answer. And that's it. Hopefully you don't think that's too terrible. Well, and then we come to something like this. Log base 16 of 8. So there's no real nice way of going from 16 to 8 in terms of powers. But what we can do is this is where you do want to turn it into an exponential equation. If you look at this as 16, that's your base. 16 to some power, let's call that x, is equal to 8. Let's think about it like that. Well, if I'd given this to you on any other day, just this guy that's right here in pink, you would rewrite each side of the equation as a power of the same base, right? So we can rewrite 16 as 2 to the 4th power to the x. 8 is 2 to the 3rd. And now you've got powers to powers right here. So you end up with 2 to the 4x is equal to 2 to the 3rd. And as we've been showing over and over, as soon as these guys have the same base, you can now set those powers equal to each other. So 4x equals 3. Divide both sides by 4, and x is equal to 3 over 4. Okay, so that's when we turned it into an exponential equation. But make sure that you come back up here and you write your answer. And the answer is 3 over 4. Now there is another way of tackling this problem using the change of base theorem, but we're going to get to that another day. It actually makes it really, really easy, as long as you know how to work it well. All right, finally, let's look at this guy. Log base 1 over 36 of 216. Looks kind of crazy, right? Well, let's see if we can rewrite this. Now, it really will be in our best interest to rewrite this using an exponential equation. So think about this as you're taking 1 over 36, you're raising it to the x power, and you're supposed to come up with 216. All right, so what's the common base? Well, the common base is 6. You look at 36 and you see what its components are. It's 6 squared. And if you look at 6 to the 3rd, you see that that is equal to 216. So I can rewrite this not as 6 squared, but as 6 to the negative 2nd power. Remember, going into the denominator is going to give you a negative power. 216, we know from our power sheet, is 6 to the 3rd. All right, and very much like the last problem that we did, you've got a power to a power. So we have 6 to the negative 2x is equal to 6 to the 3rd. Since these bases are exactly the same, we set the powers equal, so it's negative 2x equals 3. Divide both sides by negative 2, and we get negative 3/2. All right, so the answer here is negative 3 over 2. And so for these last two problems, you saw that the best way of handling them is to convert them to an exponential equation and then solve it just like we've been doing. Now, again, later on, when we talk about the change of base theorem, it gives us a slightly easier way of tackling these problems. So you don't want to miss that one.